It is a pleasure to be back here, and today I will talk to you about a new concept and algorithm in concurrent reinforcement learning, and we will see how this new concept enables rapid learning of effective policies when we have complex goals and multiple agents learning to operate in a parallel environment and collaborating with one another in real time. And this work is part of my PhD thesis at Stanford University and is done in collaboration with Professor Ben Van Rooij. So say, for instance, that we have a farm of robots that learn how to carry out a task, for instance, learn how to grab objects, and a large number of robots can gather and share a much larger amount of data in the same amount of time than a single robot. So when we have a robot that is part of a group, this robot can learn much faster than a single robot learning on its own. There are benefits to scale, but in order to make these benefits more dramatic, we need to coordinate the way the robots explore their environment. So say, for instance, that the task is to learn how to swing up, balance upright, a pole that's attached to the cart, while we want to center a cart between two walls. The cart moves on a rail between these two bouncing walls, and the pole starts hanging downwards. The robots can take three actions. They can tap the cart left or right, or do nothing. And tapping incurs a tiny cost. The rewards in this problem are very sparse, and only when the pole is steady and balanced upright and the cart is centered between the two walls, only then we observe a reward. Otherwise, the robot observes no reward. This is, in fact, a very difficult variant of the well-known cartpole problem in OpenAI team. And the difficulty from this problem comes from the very large sparsity of the reward structure. So this is a hard problem calling for deep exploration. And by deep exploration, I mean that the exploration strategy that the agent employs needs to take into account the effect of an action to future learning. It needs not only to focus on immediate information gain. In fact, it may need to incur losses for multiple time periods before anticipating gaining some information or observing some reward. And in the single agent version, one agent, depending on its exploration strategy, may need from many hours to an exponential amount of time to solve this problem. Now, imagine that instead of a single agent, we have a bunch of agents collaborating to solve the problem. Each agent has its own cartpole and controls it independently from all other agents. And the agents interact with the cartpoles in parallel, and they share data with one another in real time. Therefore, each agent has access to the information made by and gathered by all agents before making a new decision. So let's look how the behavior of epsilon greedy agents looks like. And in that example, the epsilon greedy agents train a deep Q network based on all their data. And in every time period, an agent takes the optimally predicted action by the DQN with probability 1 minus epsilon and randomizes completely with probability epsilon. And as we see, there is not much progress. Most of the robots take no action, really do nothing. And even with a large amount of robots sharing and gathering large amounts of data, again, an exponential amount of time will be needed to solve the problem. And tuning the value of epsilon, which is common in this setting, is not going to solve the problem. So instead, what is required is deep exploration and coordination of the data gathering among the agents, and this is the key to team performance. So now let's look at an algorithm that does achieve deep and coordinated exploration. We see that exploratory actions play an important role, and structured diversity of the experience may greatly accelerate learning. So with coordinated exploration, as the number of agents grows, as the number of the resources we throw to the problem grows, then a complex task can be mastered very fast. And in that particular example, something that in the single agent setting would take many hours for the best exploration strategy, it can be mastered in a matter of 30 seconds with enough resources and a good learning strategy.
The best you can hope is linear speedup, right? It's time divided by number of machines.
This would be a linear speedup always in the terms of the data. The speedup, the best you can hope is linear.
It's linear, right?
So this was seed sampling, which is the algorithm I will present today. But before we jump right in, let's look at a quick refresher in reinforcement learning. The most common paradigm in reinforcement learning is the episodic single agent tabular reinforcement learning. And in this setting, the agent interacts with the environment over episodes, and an episode marks a sequence of interactions. Once an episode finishes, a new sequence of interactions begins. In this setting, the environment is modeled as a Markov decision process, where S is the state space, A is the action space, rho is the initial state distribution, P is the transition structure, the transition dynamic from a state we take an action transition to the next state, and R is the reward structure. And if we knew P and R, it would be great. What we could do to find the optimal policy would be to solve a simple dynamic program. But in practice, we do not know P and R, and we need to learn them. So the most efficient exploration algorithms in the literature, most of the literature focuses on upper confidence bound approaches. In the upper confidence bound approaches known as UCB in the contextual bounded literature, when you transfer it to the reinforcement learning paradigm, you form confidence bounds over P and R. These confidence bounds define the set of the statistically plausible MDPs, and at the beginning of the episode, the agent selects the most optimistic MDP with respect to these confidence bounds and follows the optimal policy with respect to it throughout the episode. Now, a growing segment of the literature has been looking at efficient algorithms that rely on posterior sampling. In these algorithms, we start with a posterior over P and R. We start with a prior, and based on the data we gather within the episode, we update this posterior. So at the beginning of an episode, the agent samples a transition structure and a reward structure from the posterior, computes the optimal policy with respect to this MDP, and follows the policy throughout the episode, and then uses the observation to update this posterior.
This would be RL version of Thompson sampling.
This would be in the contextual bandits, the Thompson sampling equivalent. PSRL is Thompson sampling in bandits, and the UCRL is the equivalent of the UCB. That's correct. So in the PSRL algorithm, a common prior over the transition dynamics is a Dirichlet prior, which is a generalization of beta as we use it in beta Bernoulli bandits. Now, with respect to the reward structure, common priors that are used that have the conjugacy property are the Gaussian priors, and every time we see a reward observation from a state action pair, we go and do the Bayesian updating on this Gaussian prior of the rewards. So optimizing the user experience in a web service can be seen as a reinforcement learning problem. And we think of a web service that wants to serve targeted content to its users. And for instance, we know that YouTube wants to recommend videos to the users. But depending on who the user is and what is the history of interaction with the users, the web service wants to customize its recommendations. So there is a question of not only what to show, but in what sequence. So for example, for some users, it may be best to show some flight simulator videos and then recommend some real flight documentaries. And the web service has to do these recommendations in a way that maximize the user lifetime value or the user satisfaction. So there is a notion of delayed consequences in this problem because of the importance of sequencing and recommendations. and therefore we need to use reinforcement learning to find the optimal policy. Now, let's jump on the concurrent reinforcement learning setting, where instead of a single agent, we have K agents learning to operate in different instances of the same environment. Again, the environment is modeled as a Markov decision process, and the agents interact in parallel, synchronously or asynchronously, over a large or even infinite horizon, such as the web service interactions. Interactions with the customer may not have a predefined horizon of termination. So the K agents start with a common prior over the transition structure and the reward structure, and there is perfect information sharing among the K agents. So the K agents communicate all their information in real time and update their posteriors. So in any time period, the K agents have the same beliefs. And the goal of the group of agents is to maximize the group's total discounted reward. In the web service example, one can cast it again as a concurrent reinforcement learning setting in the notion that each user is served by another agent, and this agent is responsible only for the interactions with that user and interacts sequentially with him over the user's lifetime. So each agent aims to maximize the satisfaction of the user, but there is a commonality on what the different agents aim to learn. So they need to communicate their observations. Before making a recommendation for the user it serves, the agents learn from the interactions of either other agents who serve similar users. So in every time period, all our agents have access to the same knowledge and beliefs, which is constructed based on their collective experience.
It is something that you will explain, how you measure, how you model the similarity of users and things like that?
The similarity of users can be in the sense of having the same preferences. For instance, this talk will not dwell deeper to that, but you can think that, for instance, if the users have liked similar videos.
In terms of the modeling of the RL, of the MVP, are you making such assumptions like?
So in that case, you could use it as a state information if you want to say like the likes that a user has done could be part of the user state, and there can be some aggregation to the same state, and that can encode similarity of users. If we want to go to more high-dimensional settings, we can model state similarities through value function approximation, where we have a parameterized value function that encodes a similarity.
This is the assumption that you're making, that you're about to make, or in the subsequent slides?
No, I'm not going to assume more about the user state. So prior work has looked at optimizing for multiple users. The contextual bandit work has been very successful when we are interested in immediate rewards, but it is not appropriate for the sequential case. For instance, when we had delayed consequences that we do want to take an action for a user in order to bring him in a state where we can collect even higher rewards in the future. So if we want to deal with delayed rewards and loss-making actions in the present so as to be better off in the future, then we need to look into reinforcement learning. And one approach has been to use Monte Carlo learning, where you wait until the end of a sequence of interactions before you are able to learn something from that sequence. But now, when you have continuing problems, this is not practical, because in order to learn something, you need to wait for the sequence of interactions to terminate. So the concurrent learning setting was introduced by Silver et al., and is a suitable paradigm for this kind of problems. And since then, some algorithms have been proposed, which are all based on the optimism in the face of uncertainty, or UCB approaches. But as we will see, the UCB approach is not suitable in the concurrent learning setting, and sometimes it can do very bad. Now, concurrent reinforcement learning has also been used in robotics, but mainly as means to gather more data in the same amount of time. And considering its importance, the issue of coordinated data gathering among multiple agents, this issue has received surprisingly little attention. So our work aims to structure and coordinate this exploration in an efficient and robust manner. We have identified 3 properties which are necessary for efficient coordinated exploration, and these are real-time adaptivity to the information and experience gathered by the agents. For instance, before an agent takes an action with respect to the user it serves, it needs to take into account the observations of all other agents' interaction with their users. The second property is commitment of each agent to carry out action sequences that reveal new information. As we said before, it may be important to sequence the recommendations in some way. It may be important for an agent to commit in treating his user in a certain way for a period of time long enough in order to reveal new information or observe a reward. And finally, the third property is diversity. The agents need to diversify among the learning opportunities they pursue. So agents that serve users in the same state, they need to diversify on how they are going to act with respect with those users in order to contribute valuable information to the learning of the group. So as we will see next, these properties are necessary for building reliable reinforcement learning algorithms in the concurrent setting. And despite that, the straightforward extensions of the efficient algorithms from the single agent literature, such as the UCRL and PSRL I talked about, fail to satisfy at least one of these properties. So it's not straightforward to extend UCRL and PSRL in a way that satisfies these properties in a straightforward manner. So let's look how the optimistic approach would look like in concurrent reinforcement learning. It would be that at each time period, the agents form the same confidence bounds based on the same shared collective experience, and therefore they are going to choose the same optimistic MVP. The problem with this approach is that it's deterministic, and based on the same information, all agents are going to form the same optimistic MVP, and from the same state, they are going to take the same action. So they do not really diversify on the learning opportunities they pursue, and they do not divide and conquer when there are multiple facets of the environment to explore. So in the web service, like in the YouTube example, the optimistic concurrent agents, they're going to take the same action for all new subscribers. And in order to make the problem of optimism in concurrent RL more concrete, let's look at this toy problem at the bottom, where we have multiple parallel chains. Each one of the agents need to choose which chain to pursue. And everything is known in the setting, apart from the rewards of the last edge. So the agents know that the rewards of the last edge are normally distributed with mean zero and a variance that increases as we move from the top chain to the bottom one. Now, in this setting, the most optimistic chain is the last one. And what concurrent UCRL is going to do is to divert all the agents first at the last chain. So the agents are not going to gather valuable information that will help in the identification of the best chain fast enough. Now, if we consider of extensions of PSRL in concurrent reinforcement learning, we will realize that extending PSRL is also not straightforward. One extension one can think of is to say at the beginning of learning, like in the episodic setting, each agent will independently sample a model of the environment, and this model will be distributed according to the shared posterior, but this model will not change throughout learning. It will only change at the end of learning based on the collective observations. But as we will see in this setting, during learning, each agent does not adapt to the vast amount of data gathered by their peers. It would be in the YouTube example as if the agent serving a user would not benefit from the observations made by other agents on similar users. Now, if we want to have this real-time adaptivity, another extension we can think of is Thomson resampling. And in Thomson resampling, each agent would independently sample a new MDP from the common posterior, a new model, based on the collective experience up to that time. So the agent controlling a user's account before taking any action is going to draw an independent sample of the model to incorporate the new information gathered until the last time it took an action. But by doing this independent resampling of a model, the agent does adapt to the latest information, but it may break its commitment to action sequences that span multiple time periods. The model that the agent draws today, due to randomness of independent sampling, may be vastly different from the model it drew yesterday. So if it was important to sequence the recommendations in some way, this extra randomness due to independent resampling breaks the agent's commitment, which is crucial in environments of delayed consequences such as reinforcement learning. And to understand, again, the problem of lack of commitment, consider this example of a chain where everything is known in this chain, the negative reward in the Middle Ages, and what is not known is when we have the last edges that have opposite endpoints of large absolute value, we don't know which endpoint has a positive reward and which endpoint has a negative reward. So this is the only unknown of the parallel agents, whether they should go left or right to gather the large positive reward. And when the agents start in the middle of the chain, they start by sharing a prior that assigns equal probability to the reward being positive on the left and the reward being positive to the right. And by Thomson resampling, what they will end up doing is in every time period, they will resample a new model of their environment, but this independent sampling may change in their models which endpoint has a positive edge and which endpoint has a negative one. So in one time period, the positive edge may be on the left, they flip the coin and they say the positive edge is on the left, so let me go left. And in the next time period, the positive edge may be to the right, purely due to randomness, and this will cause dithering among the agents. And as we will see next, maybe here the problem is that they resample even without needing to, without new information, but even if the agents resampled with updated posteriors, this lack of commitment would pertain and would cause problems. So this is why we propose seed sampling, which is a novel extension of PSRL that does satisfy the adaptivity, commitment, and diversity property. And the way it works is that at the start of learning, each agent draws independently a random seed. And this seed is unique to each agent and remains fixed throughout the course of learning. The seed intuitively means how the agent is going to interpret the information. And now this seed is mapped through a deterministic function mapping, which is this GT, to a model of the environment, to an MDP. This deterministic function in the middle is common among all agents and reflects the common beliefs of these agents as formed by the collective experience. Now, because the seed is independent and random, even though the agents have common beliefs, in the end they're going to end up having different MDPs, and this will contribute to a diversity in the way they explore the environment. And the fact that the seed remains fixed throughout the course of learning, it means that the randomness injected in the sample is fixed at the beginning, and then when we update the deterministic function through history of observations, we do not allow extra randomness to change completely our beliefs. And the fact that the seed remains fixed is going to ensure in that way the necessary degree of commitment. There are multiple ways one can implement the above framework. This framework is general and can be applied to any prior or likelihood functions. Here I show 3 possible ways for the most commonly used priors. So for instance, if we wanted to sample a transition structure with a Dirichlet prior, all agents start with this Dirichlet prior that have parameters alpha 0. Based on the collective experience at time t, the parameters of the Dirichlet are alpha t. And now we know that the Dirichlet can be interpreted as a gamma over a sum of gammas. This is a Dirichlet sample. And the gamma itself can be sampled through a sum of standard exponentials. So if the agents sample at the beginning of learning sequences of standard exponentials, which they keep fixed, as the parameters of the Dirichlet changes over time, then they map these sequences through the deterministic function, and they get a sample that is distributed according to the Dirichlet posterior. And one easier case is the case of standard Gaussian seeding, where we have rewards that start with a Gaussian prior, and at time t, all agents share the same parameters of the posterior, but each agent has started with a standard Gaussian seed and uses this known equation to get back a sample from a Gaussian prior given a standard normal seed.
So from the Gaussian seeding, the intuitions that the Z says how much risk you assume in each stage. And then they commits to be very risky on that stage and very not risky the other stage, and then they.
Yes, the seed can have this concept of optimism versus pessimism, or risk or versus not risk, and the most the seed that is closest to this interpretation is doing uniform random seeds from 0 to 1. This can be interpreted as quantiles in inverse transform sampling. So if you're lowering the quantile, you can say I'm more pessimistic. If I'm on a higher quantile, I'm more optimistic. So it can have directly this interpretation.
The Gaussian kind of seems like that's how much you're adding the variance.
Exactly.
Also, that's also
exactly. Yeah, and one can also get a sample from the Gaussian with the standard Gaussian seed, or they can use a uniform random seed that I don't show here with the inverse transform sampling mechanism, or they can do this notion of Kalman filtering to get back a sample from a Gaussian posterior, and that particular way to do seed sampling has the extra desirable property of being a martingale that can be favorable to the analysis of the algorithm later. But apart from this seed,
Can I ask for an innate question perhaps? Why can't you use the same seeding technique for upper confidence schemes?
So in the upper confidence scheme works on the premise that with the confidence bound I'm going to have, I'm going to get the most optimistic MDP.
Right.
So I would get, Z there would be, if we are in a Gaussian distribution, we can take the most optimistic, say the 95th percentile. This means that if all agents take the 95th percentile, they would have the 95th.
Well, but you can improvise something, right? If you inject some seed over there, you will have like a distribution as well.
So one way to do seeding with confidence bounds would be to form your confidence bound and say, from this confidence bound, the seed is going to be, maybe I can discretize my confidence bound, it's going to be a particular region of my confidence bound that an agent can look like. Now, and that's a bit of more
It's a lengthy answer.
No, but it's an interesting discussion because it goes back to why PSRL in practice, Thomson posterior sampling for reinforcement learning, ends up being more effective than UCRL, even though they have the same regret bounds. So UCRL, the way to form the set of statistically plausible MDPs, effectively, you can think of the confidence bounds as an ellipsoid. Now, constructing these optimal confidence bounds that the authors used in their initial analysis to prove the regret bound is an NP-hard problem. It's very difficult to form these ellipsoid confidence bounds. And these confidence bounds are approximated by boxing around the ellipse. This is very easy to create these confidence bounds, but with the square confidence bounds, you're going to explore more when you shouldn't have. And in practice, because you cannot afford to form the NP-hard confidence bounds, you're going to form the box ones. In practice, UCRL is going to work worse than PSRL, but with the accurate confidence bounds, it could work a bit better. Now, think of seed sampling with the confidence bounds. We know that it's difficult to form the accurate confidence bounds. We are going to compromise with a box. Now, with the box, we can do some sort of seeding, but doing seed with confidence bounds because of the lack of accuracy in our confidence bounds, in practice, is going to work worse than doing seeding with sampling.
You try this one in practice?
It came up in ICML when I was presenting in an interesting discussion. That's the intuition we came up with, but it's an interesting experiment to run. I will definitely have it. I will definitely have it in the extended version. But yes, that's a very accurate question, why you cannot do seeding or why wouldn't you want to do seeding in UCRL. So these are some ways to do seed sampling, but the seeding mechanism, as I showed it before in the diagram, transcends specific schemes such as these ones and offers a general framework in designing reliable algorithms in concurrent reinforcement learning. So the heart of seed sampling can be summarized in these 3 points. We get adaptivity by updating the deterministic function in every time period based on the history of observations up to that time period. The fact that the agents start with an independent random seed helps diversify the exploration of the environment even with access to the same beliefs. And number 3, the fact that the seed is intrinsic to the agent and remains fixed throughout learning ensures the necessary degree of commitment. That's the 3 takeaways of seed sampling and intuitively why it satisfies the 3 properties. So to illustrate the behavior of the different approaches, let's look at an animated demo where we have as an environment a large maze. And somewhere in the maze, we have a large round of cheese. Now, the cheese can be in any of these question mark locations, which I hope you can see on the maze, and the cheese can be there with equal probability. And now we have a bunch of mice navigating the maze and trying to find the cheese. The mice have a map of the maze with annotated the question mark locations, and they also have walkie-talkies to communicate in real time with each other. So every time a question mark location is explored by a mouse, all other mice learn whether the cheese was there or not. If it was there, all the mice rush to get to the cheese. If it was not there, the mice cross off this question mark location of their list. And the posterior of the mice is a uniform distribution over the remaining viable locations for the cheese. So here is, it's slow because of the transmission of the video, but here is how the Thompson resampling mice work. The Thompson resampling mice are going to sample a new location every time period, so they won't go anywhere. Now, one can think of an improvement on Thompson resampling, where instead of resampling a question mark location in every time period, you only resample when a mouse goes and explores a question mark. So when the mouse goes and explores the question mark, the posterior of all other mice are updated, and the mice say, okay, let me resample a new target to explore. But this means that the mice may drop the target they were pursuing halfway because another mouse explored the question mark somewhere. So this Thompson resampling shows that they cannot commit and they delay a lot to find the cheese. Now, the optimistic mice are very optimistic, and they say the cheese cannot be far enough from where we are, So let me rush to the closest location of where I am. But then they don't divide and conquer along the maze, and they delay a lot in the discovery of the cheese. Eventually, they get to it. And now we have a seed sampling where the mice, they both diversify and they commit, and they find the cheese very quickly. Now, what the seed is in that case, the seed could be that at the beginning of exploration of the maze, the mice start with a random permutation of the question mark locations. And every time a location is updated, every mouse crosses off this location of the list. And the mice pursue the question mark location that is at the top of the randomly permuted list, and it hasn't been crossed off. So they commit, but they also diversify because of the random permutation initially. So with the parallel chain example, when I discussed the concurrent UCRL and the problem of concurrent UCRL, we demonstrated the importance of diversity property and seed sampling with the independent seeds and Thompson resampling with the independent MDPs, the independent models, are able to diversify in that setting, and in that setting they do well. However, concurrent UCRL does not diversify. And we,
that's fair. No, but so my question is that and maybe it comes later, but do you actually can get any theoretical guarantees for those methods?
Like, for seed sampling? Yeah. Yes, we tried over a couple of ways. It becomes quite challenging to prove something, and we have found it quite challenging to prove. And the reason for that is the fact that in every time period, because of your updated posterior, you change your model. Now, a cornerstone of the analysis of PSRL is the fact that the MDP remains fixed throughout a time period. And because you don't change it, the mistakes you're bound to make with that MDP is bounded. Now, say that in the middle of the episode, you obtain some information, you realize that the MDP is not what you drew initially, it's kind of changed. Even if in hindsight, you are more correct with respect to the MDP you drew initially, you make a lot more mistakes, which you cannot bound them. And that makes the analysis very difficult, the fact that you change it in every time period. We have a hunch that the Martingalian property of standard Gaussian seeding, this Kalman filtering idea, can help establish optimism and overcome the hurdle of changing the policy. So we are pursuing this path of trying to do analysis, but an analysis of that would be very interesting for us, but it happens to still be an open problem. With, for instance, Thompson resampling, as I will show in the next time period, there is a counterexample like the bipolar chain, the one that changes the opposite and negative reward, that you can show in that setting, it can have linear regret. So we have a counterexample, we know that this will not work. But in the concurrent UCRL setting, we see that when we have a fixed number of agents here, we plot the cumulative regret of the agents when we have the agents sorted in increasing time they left the source. And we see that the seed sampling and Thompson resampling, because they can diversify, they reach the point of zero regret much earlier because they have explored thoroughly all the chains, whereas concurrent UCRL, because it doesn't diversify, it gets to the point of zero regret only for the last few agents. And on the right plot, we see that throwing more sources to the problem, so on the x-axis we have the number of parallel agents collaborating to solve the problem, does not really help solve the issue of lack of diversity, and concurrent UCRL doesn't benefit much from the existence of its peers to decrease the average per agent regret, whereas for seed sampling and Thompson resampling, which can diversify in this example, increasing the number of agents slowly decreases the per agent regret towards zero. And now here in the bipolar chain example, we demonstrated the importance of commitment property. So when your uncertainty is whether to go left or go right, you need to be able to commit to explore either endpoint. The seed sampling, because of the fixed seeds, and concurrent UCRL, because of the deterministic nature of the algorithm, do commit to go either way and explore either way. But Thompson resampling agents are trapped to dithering left or right around the start. And for a fixed number of agents, we see here that they have a linear regret, whereas seed sampling and concurrent UCRL have much smaller regret. And now we also see on the right graph that increasing the number of resources thrown to the problem can help increase the average per agent regret to 0, whereas it does not help really solve the issue that Thompson resampling causes.
Why is concurrent UCRL changes with the number of resources? Because in other mice would just go to the same place.
You mean the right graph?
The yellow one. Yeah.
Oh, you mean why it decreases?
Yeah.
Oh, so when you have more and more agents, and you have this asynchronous progression of the agents, because of the asynchronicity, an agent can get faster to either endpoint, and then it's going to tell all the agents that are behind him, hey, guys, the correct reward is on the other side. So more and more agents are going to have 0 regret. So the average per agent regret is going to go to 0. And in that particular problem, the importance is not to diversify, because either way, the important part is to explore an endpoint of the chain. And this is why by increasing the resources and being able to commit to explore an endpoint, you get to a point where as you increase the number of agents, the regret goes to 0. Now, the examples I showed you before are toy stylized settings trying to make the point of this properties. We now revisit the cartpole problem, which is a more complex problem and realistic in terms of reinforcement learning. So we simplify the problem in order to make it suitable for a tabular setting. We want to increase the dimensionality of the state space. So we remove the walls and we make the rail infinite, so as the positional translation doesn't matter. The only thing that we care about is the angle of the pole from the upright position and the angular acceleration. And we compare seed sampling with 3 baselines, which is the concurrent PSRL, the concurrent UCRL, and the Thompson resampling. So we give each agent its own cartpole, and we let it interact with its cartpole for 20 seconds. And at the end of this learning period, we evaluate what the different agents learned. So we see that as the number of parallel agents grows, seed sampling is able to increase its rewards much faster and achieve high rewards only within 20 seconds, whereas concurrent PSRL, which doesn't adapt, and concurrent UCRL that doesn't diversify, and Thompson resampling that doesn't commit, they don't increase the reward at all as we increase the number of resources onto the problem, or they increase it very slowly. So seed sampling and the algorithm I just presented are a conceptual advance, but because it is limited on the tabular setting, it is not suitable for more of the practical problems. Like we saw before, that when we have a transition structure and a reward structure, the dimensionality scales quadratically and linearly with the number of states. But when we have enormous state spaces, we cannot rely on tabular approaches. But the seed mechanism is a general idea itself, and the goal now is to extend it from a tabular setting to a setting that can accommodate intractable state spaces, and for that we use seed sampling coupled with generalized value functions. And with value function learning, oftentimes referred to as Q-learning, each agent has a state action value function, Q, which is indexed by parameters theta. You can imagine that the Q function is a neural network with weights theta, or a linear representation with coefficients theta, we see that the generalized seed mechanism looks a lot like the tabular seed mechanism. Now, instead of having deterministic function mappings, in the middle we have value function learning parameters, and these generalized value functions can accommodate intractable action spaces, whereas the seeds control the way these value functions are fitted to the history of observations in order to interpret the same history of observations a bit differently and be able to diversify. So again, under this mechanism, each agent is instantiated with an independent random seed. This seed remains fixed and is intrinsic to the way each agent interprets the same information. For instance, this seed can be that each agent can independently and randomly perturb the rewards in the buffer. Or also a seed can be the different initialization of each agent's neural network or linear value function. And this randomness that is encapsulated through the seed and affects either the initialization of the value function or the way the history is interpreted is the one that induces a diversity. And again, the fact that these perturbations remain fixed throughout the course of learning ensure the commitment property. And finally, the fact that we have generalized value function representations instead of tabular representations, the agents are able to adapt to observations that are much more high dimensional, such as the observations from the camera of the robot, or a very high dimensional state space of a user, including its preferences, its history of interactions, etc. And one can suggest many algorithms to do seed with generalized value function representations. Least square value iteration is in the single agent setting known as an algorithm that computes a sequence of value functions reflecting the optimal expected reward over an expanding horizon based on the observed data. Here we see that the seed is used to perturb the next target Q value, and the new theta parameters are personalized with respect to each agent while adapted to the buffer of observations. And one can also come up with first-order algorithms in the vein of stochastic gradient descent, such as temporal difference learning, again by using the random perturbations as a different means of interpreting the history, and the random initialization of the Q network to induce diversity in the initial stages of learning. So when we propose new algorithms, instead of going and testing them instead of on a new test bed, it would be good to establish some sanity checks with respect to the existing tabular approaches. We see that even though the generalized value function representation seed mechanism do not have the expressive, do not have the richness of informed priors, and they are not custom tailored for tabular settings, they end up doing very close or identically as the tabular counterparts in the two toy settings. And we also scaled the evaluation of the seed sampling mechanism with generalized value functions in the full cartpole problem I showed you in the beginning, the one with the walls where we have now a four-dimensional state space with the horizontal translation, the horizontal acceleration, the angle, and the angular velocity. And we see that as we increase the number of robots trying to solve the cartpole problem and varying it from 10 to 30 to 100 to 300 robots, then seed temporal difference learning can attain very high rewards only within 30 seconds. That was a video I showed you in the very beginning of the talk. As a baseline, this black line over here is the epsilon greedy DQN agents, which again, they have as many data as the 300 seed sampling agents, but because they cannot coordinate their exploration well enough, they cannot observe any reward. So to conclude, concurrent reinforcement learning is poised to play an important role in a wide range of applications, which haven't explored yet, but some of them can be web services or autonomous vehicles or robotics, where in web services you have an agent serving a user. In autonomous vehicles, you have one agent controlling a car, and in robotics, you have an agent controlling a robot. Seed sampling, both its tabular version and mostly it's the generalized version, by satisfying the adaptivity, commitment, and diversity property, is able to achieve and learn complex goals as we increase the number of resources we throw in the problem. And this is why we think that with seed sampling and many concurrent agents, we can crack complex problems very quickly. So thank you very much. And for more, these are the two papers. Questions?
Can you go back?
Go ahead. Go ahead.
And can you go back 5 slides against that expanded horizon equation that you perturb with some random noise?
LSVI?
Yeah, if you remove the random noise, how well it performs if you just rely on perturbing the initialization of horizon?
So this goes back even to the single agent LSVI. If you remove completely the noise, then you cannot do any exploration. It's just Q learning, and then you need to do exploration additionally with epsilon grading. So LSVI is used for DQNs without noise perturbation, and then in order to induce exploration, you do some epsilon reactions, but without the noise perturbation, you cannot perform this deep exploration I talked about in the very beginning, so it won't work well.
But can you just rely on the different initializations of the layer?
When you have, so the single agent will only explore based on its initialization, but then he will not keep exploring throughout the horizon, only initially. Now, if you have so many agents, if your number of agents grows to infinity, you can rely on some of the initial exploration, the initial stages of learning. But remember that the initialization of the weights only matters when you don't have enough observations. The moment when you get enough observations, most of the weights are going to converge to very close values that are dictated from your history. And the moment this happens, then you don't have any exploration at all.
Another question or comment. Another way of enforcing diversity across the agents is to sort of think of a communication structure of the agent, which is not a complete graph. Everybody sees everybody else's. But you have like a communication, let's say a graph that you draw at random, or let's say with some process, and this will enforce diversity at the very least, because the graph may change over time, etc. Have you thought about this thing?
Yes, actually it's detailed in the second paper, and this is the version of bootstrap, way to do a bootstrap exploration, where even though you have the same history, the way you induce exploration is by masking out some of the observations. But in order to maintain commitment, one other thing to have in mind is that when you included one historical observation, you should be including it throughout learning. Once you decided to exclude it for an agent, you should be excluding it throughout the course of learning. But this bootstrap-based sampling of the history can definitely induce diversity.
Because another thing that, another concern you may have is the communication costs here, right?
Yes, yes.
You want to take into account.
And this kind of real implementation considerations are also discussed, because you don't expect, if you have so many agents, you don't expect their communication latency to be zero. The information transfer is not instantaneous. And one way to work with that is to say that every agent can be operating in one processor or one machine, and it has its own copy of the buffer. Over time, as an agent makes an observation, it broadcasts it to the agent. Now, the moment that another agent is about to take its action, this observation that was just broadcast, it may have arrived, it may not, but the agent just goes ahead with whatever it has in his cache, and that way you don't expect them to be perfectly synchronized in terms of information. Now, if you want to have them control the amount of asynchronicity you allow, you can do, from the systems literature, you can do some kind of barriers, synchronization barriers, where you synchronize the amount of information the agents have every, say, n time period.
You don't need the seeding anymore, right? In this case.
Oh, the seeding, like the bootstrap you described, is a form of seeding, because the seed is what
you don't need the seeding in the explicit form.
Exactly, because it is what in the seed now is which indices in the buffer you're going to be using for your training. So it's often that you cap your buffer, say, to 500,000 observations, and then as initial seed, you can say they are in indices, bootstrap indices, which remains it. So that's again a seed.
So in order to get like a model here for which one can prove something, what's the toy model? Like, have you thought about some, like we are talking about like MDPs that have to collectively learn in a diversified manner so you can get much faster convergence. So like, can we simplify the model in a way that, like, so what's the fundamental theoretical problem here?
So one thing one good starting point would be that you start with a tabular representation, an MDP, where you say, I have known transitions, dynamics, my only unknowns are the rewards, and I start with this type of Gaussian prior on my rewards shared among the agents, and the agents update their posterior of the reward parameters by doing this form of Kalman filtering. We think that that's the minimum viable starting point of a model to prove something, and the fact that you have the martingalian property may facilitate that, may help. Now, I don't know, this has proven quite challenging. Initially, we thought it would be very, not very easy, but kind of manageable to prove something. But the moment where you start randomizing by adding noise, even when I looked more in the literature, it seems that in general, even in the single agent, it's very difficult to get theoretical guarantees when you do exploration in terms of random perturbations. And the only guarantees that exist up there are on for single agent are on randomized least square value iteration, where it perturbs the rewards with standard Gaussian noise. But then the only guarantee, even though this algorithm is general, the only guarantee is on tabular version, linear representations, and only one hot encoding feature. So it's very restricted what you can prove. The moment that you try to generalize, it just gets messy. But if this bright group has other thoughts about proving seed sampling, it would be of great interest of me to discuss more.
Thanks a lot.
Okay, thank you.